So continuing with our lectures on quantum mechanics, on this video we'll go through a few new rules. So just to remind us, we've only had 2 rules in quantum mechanics so far. A little abstract, but those are our only rules. So I want to add a 3rd rule here, and that is for every observable, what is an observable? Something you can observe, whether it's the position is something that's observable, the momentum, the energy, the angular momentum, anything that's observable right there. For every observable, there is an associated operator. We'll call it, we'll put a little caret on it, operator. So for everything you ever wanted to measure, there's some sort of an operator associated with that observable. Now we might say, what the heck is an operator? Operator operates right here. So if we have something like 2 and we want to operate on it, we can say, what would my operator be? It could be something like 3 plus. That's an operator. What does it do to 2? It makes it 5. What does it do to a star? It makes it 3 plus star. What does it make to anything? 3 plus anything. Or it could be, you could operate on a function. If you have some function of x, what you could do is you could take the derivative of it. That would be an operator, the derivative with respect to x. You could integrate it. You could take the reciprocal of it. I don't know. But that's just some sort of a mathematical operation. That's what we call by an operator. So for every observable, there is some sort of operator associated with it. That's number 3. And then we have number 4 here. If we now use that operator and operate on our state, we get lambda times back our function, or our state. Remember, we already did this when we were looking at the math right here. We said this was an eigenvalue, eigenfunction equation. So it's very important in quantum mechanics. So since this is a column of numbers, our operators looks like they're just going to be a matrix. This is going to be a matrix right here. Okay, and so let me rewrite that over here. So we said an operator, whenever we operate on our state, we got some values out. These were the eigenvalues back our state again. And what did we say? When you calculate this lambda, you're going to get the same number of lambdas that you do as the dimension of the space. Since all of our vectors so far have only been a 2-dimensional vector, we would only get 2 values of lambda. So what you're going to get out of here is you're going to get a lambda. We could get more than that. You could get, if it was more than 2 dimensions, but matter of fact, let's just say you could get more. Lambda 1, lambda 2. What are these eigenvalues? They're everything that you measure from this operator. So if you're measuring, say, the energy, these would be all the energies that you could get out of it. If you were measuring the position, these are all the positions that you would get out. These are whatever your answers are for what you're measuring. They're all the possible answers. Okay, and then associated with each one of these eigenvalues was an eigenfunction. Say psi 1, this one will give you, say, psi 2, ... These all form my orthonormal basis vectors. right here, these four. So the operator gives you the values you get plus your orthonormal basis vectors. So before you've made the observation, you don't know which one you're in. You don't know which state you're in. You don't know if you're up or down or whatever. So before you made the measurement, you're some sort of a combination of these. This is, say, alpha 1, psi 1, plus alpha 2, psi 2, plus ... So remember, when we were, our psi, we were in a function of ups and downs before until we made a measurement. Then it became either up or down. Okay, remember, this squared, this times this complex conjugate is the probability of measuring psi 1. This squared is the probability of measuring psi 2. This squared is the probability of measuring psi 3. And when you add this squared plus this squared plus this squared, you get 1. Okay, but now, plugging it into here, remember, this gives you all the psi 1, psi 2, psi 3. Let's just say you measure psi 2. You did this measurement and you measured psi 2. What this will do, this function will collapse to this state. So if you measure lambda 2, psi collapses to psi 2. If you measured state psi lambda 1, it would collapse to psi 1. So this is just telling you every time you make a measurement, you don't know what you are. You're a combination of all of them. Just like when we were going through the double slit, when we didn't measure where the electron, which hole was going through both. But once we measured it, there's probably some operator associated with that, it collapsed it down. Okay, so let's just look at this right here, see if we can, that would mean that when we did our measurements, say, when we did this, Z, and we had the little digital sensor here, and that was a measurement. So there is an operator associated with this Z, spin Z direction right here. Let's just see if we can find out what that operator is. You know, when we did this example a few lectures ago, I gave you the operator, and we found this, and we found that. But now we do know, for this case, we do know what we measure, and we do know the states, their ups and downs. So maybe we can go back and get the operator. So for this case, what was the things we measured? Well, it was, what did the digital say right there? It said 1 plus or minus 1. But remember, that was in units of h bar over 2. So let's just say what you really measure is h bar over 2. So one of the lambdas will be h bar over 2, lambda 1. And we know when we measured a 1 what the state was. That was the up. So psi, if we collapsed to just the up. And we knew if we measured minus 1, which is minus h bar over 2, we know that the state collapsed to down. And before we made the measurement, we were in some combination of ups and downs. So before, the state psi was alpha 1 up plus alpha 2 down, where this squared is the probability of measuring up, and this would have been the squared would have been the probability of measuring down. Okay, so we're given all this information. Let's see if we can find out what our operator is, the matrix is. Okay, and we do know it's a 2 by 2 right here, because this is we only got 2 solutions. So we know that my S, we'll call it the spin in the Z operator, since this is in the Z direction. We know it's got 4 elements to it. It's a 2 by 2. How about if we just call them A, B, C, and D, and let's just solve for A, B, C, and D. Okay, so let's just come back to here, and let's plug it in. This thing right here is our operator, A, B, C, D. A, B, C, and D. And let's first operate on psi 1, which is my up, and we should get my lambda 1 back to my up again. So we operate that on my up, 1, 0. So we're doing S sub Z acting on up should give me my lambda, which is h bar over 2, h bar over 2, back on my up again, 1, 0, which was my up. Okay, so that's what this is saying. We know we can do it for the down too, but except we would plug in minus h bar over 2. Okay, well, let's look at this. This is really 2 equations up here. Let's look at, if we just put these together, what do we got? We got A plus 0, so that's, well, let's just write it as A. Actually, we'll just do it. A times 1 plus B times 0 equals h bar times 1. H bar over 2 times 1. Okay, that's just going across the top. Well, this is gone. And the ones, A is just h bar over 2. So we got A. A is h bar over 2. So we have one element of the matrix. Let's look at the bottom row right here. We got C times 1 plus D times 0 equals the bottom right here, which is 0. Well, this says that C equals 0. So we've got 2 elements of the matrix. Okay, so now let's look at the other one, the ABCD. When we operate on the down, which is 0, 1, that should give me the minus h bar over 2. Down, 0, 1. Okay, and so if we multiply this thing out, we got 0 plus, sorry, not A times 0, which is 0, plus B times 1, which is B, equals 0. So B equals 0. And then the last case here, C times 0 plus D equals minus h bar over 2. Okay, so D, this is gone, so D is minus h bar over 2. D is equal to minus h bar over 2. So I know A, B, C, D, so I know what this is. This is, A was h bar over 2. B was 0. C was 0. And D was minus h bar over 2. Minus h bar over 2. So that matrix is that's the operator associated with this measurement. I could pull out the h bar over 2. Maybe we'll do that and just make it h bar over 2, 1, 0, 0, minus 1. 1, 0, 0, minus 1. Okay, so you can either write it like that or like that. That's the operator associated with S sub Z. Now I should say that these operators, but a lot of times if you just pick any matrix, this is going to be a complex number, especially since these are complex vectors. But we never want a complex number here because we can never measure complex things. So since this always has to be real, because that's all you can measure is real things, that means that these operators, these matrices, have to be special right here. And they give a name to these special matrices that give you real values here. They call them Hermetian matrix. Hermetian matrices. One thing about these matrices are that if you take the matrix and you take the transpose of it, what does a transpose do? It doesn't do anything to the diagonals, but it flips the row columns right here. So for a 2 by 2, it flips these two, and it doesn't do anything to these. If you take the transpose of it and then do the complex conjugate of it, you're right back to your original matrix. So you noticed right here, if I take, well, these are all real, so the complex conjugate doesn't do anything, but if I just take the transpose, you notice it's still the same matrix, because all it did was switch the 2 zeros. So all matrices that you could get real values are going to follow this rule right here. Okay, well, let's go back and let's work out one the opposite way. Suppose you were given a matrix, M. I don't know what this observation, and let's just say it's H bar over 2, and it's 0, 1, 1, 0. So it's this guy instead. And ask, what is the eigenvalues and eigenvectors for that measurement right here? Actually, I can put the H bar over 2 into it. So this is 0, H bar over 2, H bar over 2, 0. You'll notice that this also is Hermetian, because if I take the transpose of it, it stays the same. And it's real, so the complex conjugate doesn't do anything right here. And so what do we want to solve? We want to solve M times my wave function equals lambda times the wave function. Remember, we solved this before. We're just going to do it again just to get a little more practice here. So what was the rule here? First, you take this and bring it over to the other side and factor out the psi. So you got M minus lambda, but I can't subtract a matrix from a number, so I turn that into lambda I, the identity matrix, times psi equals 0. And the only way this can be 0 is if the determinant of this is 0. We just set the determinant of this equal to 0. First, let's get this matrix. So this matrix is well, let's just write it as, this is 0, H bar over 2, H bar over 2, 0. And then we're subtracting off this, that's 1, 1, 0, 0, but we have a lambda, so it's lambda, lambda, 0, 0, times, well, let's leave that out. That's just this part of it right here. Now let's combine them together. So we get 0, we get minus lambda, H bar over 2, H bar over 2 minus 0 is H bar over 2. 0 minus lambda is minus lambda. Okay, so that's just your M minus lambda I. Now we just take the determinant of this and set it equal to 0. So that's just this times this minus this times this. So you got this times this is just lambda squared minus H bar over 2 squared equals 0. Oh, okay, well, looks like the solution to this is lambda equals plus or minus H bar over 2. So there's my two solutions. Lambda 1 is equal to H bar over 2, and lambda 2 is equal to minus H bar over 2. So those are my two values that I can read, h bar over 2 and minus h bar over 2. Now, if I want to go back and get the eigenfunction for these, then I can just go back to this equation. We already know what this was. This is just this right here, times your psi. You don't know what psi is. I'll just use A and B right now and we'll find it. So this part right here is minus lambda h bar over 2, h bar over 2, h bar over 2 minus lambda, times my psi, I don't know what it is, we'll just call it AB, and that equals 0. Okay, now let's plug in what lambda, we'll do it first for lambda 1. So for lambda 1, it's h bar over 2. So that means we've got minus h bar over 2, h bar over 2, h bar over 2, minus h bar over 2, AB equals 0. So if these are just two equations, this tells me I get minus h bar over 2a plus h bar over 2b is equal to 0. The other one's going to give me the same right there. What does this say? This says that a must equal b. A equals b. Well, if a equals b, we know what they both are. They're 1 over the square root of 2. So it looks like my state psi 1, the one that's associated with this, so lambda 1, which was h bar over 2, the psi 1 was just 1 over the square root of 2, 1 over the square root of 2. Well, heck, that was just my right state, if you remember. That's just my right state. And then when I plug in the minus here, h bar over 2 up into here, this is going to be plus h bar over 2 plus another h bar over 2. So now let's plug in the other one right here. If we plug in, I guess I'll just plug it up right here next to it. If we plug in the other one, the minus, then this would be plus h bar over 2, h bar over 2, h bar over 2, h bar over 2. This would be plus h bar over 2, AB equals 0. Oh, this says h bar over 2a plus h bar over 2b equals 0, so that says a equals minus b. If a equals minus b, then one of these has to be a minus, and it looks like we can just make the bottom one minus. And so my other one was lambda 2, which equals minus h bar over 2, psi 2, look like 1 over the square root of 2 minus 1 over the square root of 2, which was my left state. So it looks like this matrix right here was really my S for the x direction. This right here was just S in the x direction, right there. There would be one for the y too. So there is the Sx and there's the Sy right there. Okay, now I want to add another rule over here. I don't know if it's really not a rule. I could really derive it, so it's not an independent rule. They might not even call this a rule in quantum mechanics, but I will right here. Suppose you wanted to find the, let's say you have a I don't know, whatever you're measuring. Let's say this thing is what you're measuring. And you have a whole bunch of identical state psis. They're all identical right here. I don't know what they are. They could be rights and lefts or ups and whatever they are. They're all identical. And we come along and measure for the first one. And I don't want to measure the first one again because I've affected it. But then I'll throw the second one in a measure and see what I get. Put the third one in, see what I get. Put the fourth one, the fifth one. And I want to know what is the average value of this if I did this for a whole bunch of them all that were the same. what would be the average value? And so that's what I call this rule 5 right here, rule 5. It says the average value, the average, the book won't use average. Most books use another word. They use the word expectation. I don't like that. Expectation. I'm just going to use the average. That's all it really means. You get from many measurements, you get from, say, many measurements, you get from many measurements of identical systems, of identical systems is given by, and so what you do is you take your psi, you put your operator in there, whatever you're measuring, in your psi like that. This is like making a sandwich. There's the meat, there's the bread on the two ends right there. And this, and just shorthand notation, is you write like this, the operator. It gives you the average value of, if you had a whole bunch of them. You can't use the same particle to find the average because you've affected it by measuring it. Okay, so let's just see how you use this right here. But again, most people wouldn't even call this a rule. It's more or less just it's just the definition of average of anything. So it should have been on statistics of anything. So let's just say we have some state. Someone gave me a state that was, let's say, 1/2 up plus the square root 3 all over 2i in the down. Okay, what I think I'm going to do is I hate this thing sticking out there, so I'm just going to rewrite it right here. H bar over 2, H bar over 2, H bar over 2, H bar over 2, A, B equals 0. So I'm just going to take that and put it over here just so I have the space. I don't like this thing sticking out. Okay, and so what I'd like to do is ask, if I were to measure, take this thing, a whole bunch of them, I had a whole bunch of these electrons, they're all been prepared this way, a whole bunch of them, and then I take my apparatus in the z direction, and I measure the first one, see what it reads, then read the second, the third, the fourth, the fifth, the sixth, and what is the average of all those values that I read? Remember, every time I get a +1, it's really +1 h bar over 2. Okay, so what does that mean I need to do? I need to do the sandwich. The psi S sub z, which we know what S sub z is. It's right here. There's my S sub z, or yeah, we'll just use that one right there. S sub z psi. That's all we've got to do. Now, I'm going to do it 3 ways. You can pick whatever way you want. Hopefully each time they get easier. So if we do this in terms of all the columns of numbers right here, if I write this in terms of a column of numbers, remember this is really a half times 1 0, so that's 1/2. And this one down here would be I square root 3 over 2. So there is what your psi is if you want to write it as a column of numbers. Okay, so then let's do this. Now that we have that, we first need the bra of it, so we turn it sideways and we do the complex conjugate. So that first one would be 1/2, And then we do the complex conjugate, so it's minus I square root 3 over 2. So there's that one. Then we have this matrix right here, which is h bar over 2, 0, 0, minus h bar over 2. H bar over 2, 0, 0, minus h bar over 2. And then we have just our psi, which is that, which is 1/2 I square root 3 over 2. Okay, we just got to solve that. Okay, so remember, I think we said before, it didn't matter whether you multiplied these two first or multiplied these two first. They're both going to give you the same answer. So we'll do these two first. So let's keep the 1/2 minus I square root 3 over 2. Okay, so now we'll multiply those two together. So if we multiply these two together, we get h bar over 4 plus 0. Well, that's just h bar over 4. And then the other one we get is 0. We get these two multiplied, which is minus I h square root of 3h bar over 4. Square root of 3h bar over 4. Okay, and then we can just multiply the row times the column, which is h bar over 8. Okay, and then this right here, the minus I and the minus I gives me a minus 1. The square root of 3 times the square, that's 3/8 h bar. H bar over 8 minus 3 is minus 2h bar over 8, which is minus h bar over 4. So the average value that I would get if I had a whole bunch of those, the average value, remember, multiplied by h bar over 2, would be minus h bar over 4. So it looks like there'd be more downs than ups, because the downs was what brings it down a little bit. So remember, because when I measure it down, I get minus h bar over 2. And if I had even numbers, I'd get 0. So, okay, so there's one way you can do it. There's another way we could do it, this without doing the column of numbers. So if we wanted to do psi S sub z, S sub z on psi. Okay, so instead of using the column, what I think I'll do is just use this right here instead of this over here. So first, let me just do this right here. S sub z acting on psi. S sub z. Okay, so what does that give me? It gives me S sub z acting on this. 1/2 up plus the square root of 3 over 2 I down. Okay, now we already know that when I operate S sub z on up, we just get h bar over 2 back or up again. And when I operate SC on down, I get minus h bar over 2 back on my down again. So I can do this right here. This just gives me 1/2 S sub z on up gives me h bar over 2 back my up again. Plus square root of 3 over 2i, square root of 3 over 2i, S sub z acting on down. Well, that just gives me minus h bar over 2 back on my down again. Okay, so I've done that right there. So now all I have to do is add this part at the beginning. And remember, to get the bra of this, You turn these into bras, and you turn these into their complex conjugate. So just this right there, all by itself would be 1/2 bra U minus the square root of 3/2 I bra D. Okay, so that's what that would be. And so all I want to do is put that with all of this right here. So maybe I'll even add the whole thing in there. So we're going to have psi S sub z psi. So I've already done the S sub z psi is right there. So let me just put that in. So we got this here. We got h bar over 4 up plus, no, actually it's minus I minus I h squared root of 3 h bar over 4 down. Okay. Now it's easy for me to dot these two because when I multiply these two together, I get up, which is just 1, so I just get h bar over 8. And then up with down gives me 0, and down with up gives me 0, and then I just have the down with the down, which gives me 1, so I just have to multiply these two together. Minus I times minus I is minus 1, so it's minus. And then I got square root of 3 times the square root of 3 is 3 over 8. Minus 3 over 8 h bar minus 3 over 8 h bar, which gives me what? Minus 2 h bar over 8, which gives me minus h bar over 4. It gives me the same thing. Minus h bar over 4. So that's a second way you could do it, h bar over 4. Okay, that looks a little simpler than this. You don't have to go to the column matrices. And then let me go to even an easier way. Suppose you had, I don't know, just a coin right here, and if you threw a heads, it gave you say, I have the number 5. You say, add 5, say. Well, okay, you just get the number 5. And then if you get a tails, let's just say you add 8. I could subtract 8, but we could just say you get the 8 right here. And so now you just start flipping coins right here. Every time you get a head, you add 5. Every time you get a tail, you get 8. Actually, let's say you subtract off 8. Maybe that's better. And now you keep doing that. And now at the end, if you did it an infinite amount of times, and you ask, what is the average value you're going to get per throw right here? Well, how would you calculate this thing? You'd say, well, I get 5 half the time. So it'd be the probability of heads times 5 plus the probability of tails, which is a half, times minus 8. And so that would just give you 5 halves minus 8 halves, which is minus 3 halves. So the average value that I would get would be minus 3 halves every throw. That's the average right there. And I get more, it'd be a negative because my negatives counted more. Okay, so whenever you're trying to find an average, you could say it's the probability of this one times the value of this one plus the probability of this one times the value of this one. Well, if we just come right up to here, we know the probability of getting up is just 1/4. So you could have just said it's just 1/4 times the value you get from up, which is h bar over 2, plus the probability of getting this one. Well, if the probability of getting this one was 1/4, the probability of getting this one is 3/4. It's this squared plus 3/4 times the value you would get from the down, which is minus h bar over 2. What does that give me? H bar over 8 minus 3h bar over 8, which is exactly what I have down below. So this is a much easier way. It's just the probability of this one times the value you get from that, plus the probability of this one times the value you get from that. So, you might start out doing it the long way, but pretty soon you'll learn to just do it a real quick way right there. Okay, so that is another one right there. Now, there's not a lot of rules here for quantum mechanics. As a matter of fact, there's only one more rule that we're going to put. Only one more. Really, there was probably only 5 to begin with, but we're only going to have one more rule. We're not going to use it now, but I'm just going to write it down. And it has to do with how these states evolve in time. And this thing, so 6, this will be my last rule for quantum mechanics for the rest of the course. We're not going to learn any more rules. Everything just, this is it right here. We'll just apply it to a lot of cases. And it's something, it's H operator. It's a special operator acting on my psi, right there, equals IH bar times the derivative of my state with respect to time. That's it. There's all the rules of quantum mechanics. You can even take out this rule because it's not really a rule. So there's really only 5 rules at the most. Now you might say, what the heck is H right there? H is remember, it's just an operator right here, but it's to a special measurement. It's called the Hamiltonian, and it's the energy operator. So H is the energy operator. Energy operator. So they call the H is really because it's the Hamiltonian. That usually means the energy Hamiltonian. So it tells you how the state updates from the psi changes as a function of time. It has nothing to do with the collapse. The collapse is a special thing that's independent of this. So I'm not going to, how could I put this into our electron spins, Well, remember, what is this? These are electrons that are spinning. So we have an electron here. I don't know how to draw it, but we'll just say here is my electron kind of spinning around right here. It's not really like this, but we'll draw it like this. Well, if you remember from electromagnetism, if you had a loop of wire here, and you had some current going through it, I, you said that was some sort of a magnetic dipole. I don't know if you remember that from your electromagnetism. You said, I think we called it mu, and it was I times the area, where the area is this area right here, and the direction of this mu was off. It was perpendicular to the area, and use your right hand, so it was kind of going off like this, mu, like that. Okay, and then you said, well, if you put this into a magnetic field, and so remember, this has its own because there's current flowing in there, but if you put this into an external magnetic field, then, first of all, you got a torque, which was mu, this mu cross B, where B was your external magnetic field. And you also got the energy, the potential energy. I think you said it was minus mu dotted with B, right here. Those were the equations right here. Now, what do we have right here? We have a charge. Remember, electron has charge, and it is spinning right here. So this thing does have a magnetic dipole moment. right? I'm not going to give it to you what it is, but that magnetic dipole moment is somehow proportional to the spin, the angular momentum, the S. There's proportionality constant in there. It might even be in the exact opposite direction because of the minus, but that's just part of the proportionality right there. Okay, so if I put that into an external magnetic field, say a magnetic field like this, B field, then first of all, I've given it some energy because you get this dotted with the B, but there's also a torque on it right here. And what's this thing going to do? If you put a torque on it, it's probably going to precess right here. So this thing might precess right here. So if I had, I don't know, let's just say, here I brought out a tire. And let's say I come back to our spin states right here. What do we have? We have, here's our Z, and here's our X right here. And let's just say we get this guy originally pointing in that direction, and we put a magnetic field in this direction on it. And so what's this thing going to do? Once I put a torque on it, it's going to start going like this right here. That is, this state, which was all in the X direction, might all of a sudden become the Y direction, and then the minus X, and then the minus Y. So I have a way, when I put a magnetic field on this, to move the state around right here. Or if I put the magnetic field in another direction. So I can, if I want to manipulate this, the direction of the spin, put the magnetic field on for a little bit of time, okay, then take it off. Put it on another way, take it off. So you can move this state around right here. This has a lot to do with magnetic resonance right here, because I can set up a resonance here from these frequencies. But I'm not going to do this for this state. We'll use this equation on the bottom for later states, because that bottom equation is actually called Schrodinger's equation. Except it's not the form that you'll see until this is in a more compact form right here. Okay, so that's all the rules. No more rules to quantum. We're just going to apply it to everything. This works for all of chemistry. Is right there. Okay, so.